the number of absorptions per atom per second divided by the number of incident photons per square meter per second. And the reason why that's an area is because,
Because units of atoms.
well, see, here's the thing. Suppose that this is 1 meter by 1 meter. Okay? What's the probability? And suppose that the atom was a disk or a sphere that looks like a disk that is such that if a photon touches it, it's absorbed, and it misses it, it's not absorbed. Then what fraction of the photons, if they're just randomly distributed over that square meter, what fraction of them would be absorbed? Well, it would be this area of the atom divided by 1 square meter, because that's the fraction of the area that the atom covers. And so, while in reality it's not a hard little sphere, and there's more probability of absorption if you're closer to the atom, but there's still a little probability to absorb it even if you're out here somewhere. Still, you can define this ratio, the absorption cross-section like that, which will essentially then be telling you effectively how big the atom looks. What size of a hard sphere, what cross-sectional area of a hard sphere that absorbs everything that touches it would absorb the same number of photons as the actual atom does, is the idea there. So interestingly enough, notice that it depends on n inversely. The bigger n is, the smaller is the cross-section, which is a little counterintuitive because the atom gets bigger as it increases. It's further away from the nucleus. So I don't know how to justify that, but they said it's true and I believe them. So.
Yeah, it's pretty interesting.
And it's interesting to note that sigma Bf is comparable to the collision cross-section, the cross-section for the atoms bumping into one another. Of pi times 2a0 squared, right? If you just put in in our model before that we had, put in the Bohr radius and make it twice that big because it's all that, right? If you plug that in, you get 3.52 times 10 to the minus 20th square meters. So, not too different between that and 1.31 times 10 to the minus 19th square meters. They're approximately, they're not exactly the same, but they're approximately the same as one another. So in other words, the atom looks about as big to photons as they do to one another, so to speak. Which you kind of expect, because the photon's going to be absorbed by the electron, and the electron's, where's the electron? Well, it's over about the size of the atom. So.
That cross-section is what a incoming photon looks like to an electron, right?
This one right here?
Yeah.
No, this one is what atoms look like to each other.
Oh, wait, okay, I see.
That's what they look like to one another from bumping off one another. So there you would say, instead of sending a bunch of photons at the atom, you send a bunch of other hydrogen atoms at the atom.
Okay.
And you ask how many of them either collide with it or get redirected, essentially. Change their direction as a result of a close encounter. Okay, so I'm going to let you predict what the next one is going to be. So far we've got bound, bound, free. What do you think the next one will be?
Free.
free, free. The electron begins free and it ends free.
Oh, wow.
So the idea here is that, and we'll see it has to be close to a nucleus to do this, to conserve momentum and energy. But it's possible for an electron near a nucleus to actually absorb a photon and change its motion as a result of that. A free electron cannot absorb a photon, can't conserve momentum and energy. But if there's an ion nearby, a nucleus or an atom missing some electrons, a positively charged ion nearby, then the ion can pick up the recoil energy and allow this to work, essentially is what it comes down to. So the next one is free absorption. Absorption because, again, the photon disappears when this happens. The final one's going to be electron scattering, where an electron comes along and kind of a photon comes along and kind of bounces off an electron. But this is another form of absorption, which you probably haven't heard of before. But it's possible, even though there's a continuum of energies available to a free electron, ones that aren't bound to atoms aren't quantized in their energies. It's still possible, if the electron is close to an ion, to absorb a photon, to completely eat it and use that to change its kinetic energy. So free absorption occurs when a free electron near an ion absorbs a photon and thus picks up speed, picks up Ke. Near an ion absorbs a photon, photon disappears, and thus picks up speed, i.e. its Ke increases. The ion is needed so that both momentum and energy can be conserved. You can show with relativity that if you ask an electron to absorb a photon and to eat it, it doesn't work, because if the electron absorbs the photon, then the photon has momentum, so therefore the electron must have momentum after it absorbs it. But that means it's also got energy after it absorbs it. And the problem is that if you conserve momentum and you ask how much energy does the electron have, it's not equal to the energy of the photon. So you can't get it to work. You can't get it to have the same momentum as the photon and the same energy of the photon afterwards. And that's fundamentally because for a photon, the energy is Pc, it's momentum times the speed of light. But for the electron, the energy is the square root of mc squared plus Pc squared.
The
rest mass energy plus the momentum component of the energy. And so because those two expressions are different from one another, you can't get it to work, because a photon and an electron have a different relationship between their momentum and their energy. So you need to have a composite system, an ion and an electron, and then you can get it to work. Because then both the electron and the ion pick up kinetic energy and momentum, and in that case it turns out you can get it to work. So the picture we show...
So it's the presence of the ion which keeps
it's what allows
the whole process
to occur. So the picture we draw is, here's an electron, comes a photon, well, I'll have it come from this way. Here comes a photon, and you get the absorption, and the electron as a result afterwards is moving in a different direction with a different kinetic energy.
It just entirely deflects it.
Yeah, it deflects the electron and speeds it up. Or it could slow it down. I mean, I said it speeds up, but it could slow down too, in that if the electron is coming this way and the photon's coming this way, you could have the electron slow down as a result too. The inverse process, we'll take a break after this, the inverse process would be where an electron near an ion loses kinetic energy and gives off a photon.
Okay.
So it can emit a photon too. The inverse process, where an electron near an ion slows down and emits a photon.
So, okay.
Yeah, go ahead.
If the temperature is high enough, would it prevent the electron from being recaptured into the ion?
Yeah, in the deep interior of a star, where the temperatures are higher, recombination essentially doesn't work because things are moving too fast.
So if you're in the atmosphere and does this process occur in the atmosphere?
It does, because in the sun, for example, metals are easily ionized.
Mm-hmm.
And so there are free electrons that were stripped off of metals in the sun's atmosphere. The hydrogen is essentially neutral at solar temperature, solar photosphere temperature, but there are free electrons that were stripped off of metals, and so this process happens in the sun's atmosphere, example, because of those free electrons that were stripped off of easily ionized atoms. Deep in the sun's interior, the first two effects don't occur. Bound and bound-free absorption don't occur deep in the sun because you don't have any bound electrons, essentially. But this still does because you've got plenty of free electrons and nuclei swimming around, so to speak. So in the deep interior, this and electron scattering are the processes that happen. In the solar atmosphere, all four of them can happen. In the star's atmosphere, all four of them can happen. So in that sense, it's easier to do a star's interior than its atmosphere, because as we'll see, electron scattering dominates deep inside the star. So things are less complicated when it's hot.
So at higher temperature, the free dominates.
At higher temperature, actually, electron scattering dominates. There's a fourth one we haven't talked about.
Oh, that's next.
That's next, and that's the one that dominates deep down. That's right, yes. So the inverse process, where an electron near an ion slows down and emits a photon, is called a great name, Brainstorm. Brainstorm.
That's the name of the inverse process?
Yes, it is. And the reason is because it's a German word. Strahlung is the German word for radiation, and the Brenz means break or breaking, slowing down.
Ooh.
So it's radiation because things are slowing down. Brainstorm. Yeah. Brainstorm, yes. Brainstorm is the inverse process. Classically, accelerating charges radiate. So classically, what happens is you've got this ion, the electron, if a free electron just moving along a straight line is not accelerating, and so it's not going to emit any electromagnetic radiation, or for that matter, absorb it. Classically, if the electron is near a positively charged ion, it will accelerate because of the electric force that it feels. And classically, that acceleration would cause it to emit a classical electromagnetic wave continuously. And it would also do other way around. If any acceleration can cause it to emit electromagnetic radiation. Also, an electromagnetic wave could be absorbed by the electron as it's passing by in a continuous fashion as well. But the quantum version involves photons instead of continuous emission. You eat a photon or spit out a photon. So this name comes really from kind of the idea of the classical version, where it's continuously changing direction and speed as it moves past the ion, and that will be associated with radiating because accelerating charges radiate according to classical electromagnetic theory, but the quantum version of it is more discrete, essentially.
Because it treats radiation as packets. It's
packets, that's right. And so the electron eats or spits out a packet of radiation, a photon. Now, it's still a mess because, well, if you do the calculation, it's got a probability per unit time of absorbing a photon or emitting a photon, and but the picture we have is at some point that you can't predict in advance, it says, I'm hungry, and eats a photon, or I'm not hungry, and spits out a photon. So, now it's time to take a break. It's more than time to take a break, but we'll take it now.